for, okay? So far we've been talking about general attention, right? So this is the general attention. Now we learned that the attention mechanisms can be more generalized, okay? So we talked about the key ideas, right? So now, keep in mind, again, this attention was between H sub t in the decoder and Zij in the encoder. That was attention, right? So Zij was from Xij, okay? So now think about a self-attention. That's like the attention within the encoder or decoder. For instance, in the decoder or in the encoder, right? So that's when you're paying attention to. So now let's talk about the self-attention, right? So now we don't have a query at all, right? Because that was the attention between the attention on X when you do this Q, right? So when you try to figure out for the corresponding Q what attention I should put on X, right? Now imagine that this is a self-attention that your only input is X. There's no query. So it's like the attention on itself, okay? So in other words, previously, my Q was given, right? In the image captioning example, the Q are the H, is that right? From the decoder, right? Now, Q is not given. It's a self-attention on, for instance, this is an encoder, so then this is a self-attention within the encoder. That is self-attention, in X, right? It's like X paying attention to itself, right? So I still use Q, but my Q is going to be generated from X. Is that clear? It's a self-attention, right? Right? It's a self-attention. So I still use Q, but it's not given the input. It's going to be generated from X. Okay? So that's the input. That's so-called self-attention. Okay? So we can calculate the query vector from the input vectors and defining a self-attention. For instance, you want to figure out, the attention you put within these input vectors, okay? So how do you calculate the query vector? Again, very similar, like what we did when splitting the input vector into keys and values. We used a fully connected layer, a linear layer, parameterized by matrix W sub Q. So now you have the three key components of transformers that use the self-attention mechanisms, okay? There's keys, values, both related to X, but then there's also queries, also from X, okay? Let's keep us reminded again why we had keys, values, and queries all transformed from the input X, right? We have this, X transformed into queries, right? The way that it's transformed should be learned. We do this because we are doing this self-attention. That's for the purpose, okay? And then we also split the input into keys and values because we want to use the input differently in two steps. One is the alignment or similarity. One is the softmax, attention calculation, okay? Attention calculation. So that's, now you see that KVQ, key value queries are all from X with learnable parameters W, okay? Their forms are all the same. This is, matrix, this is a vector times a matrix, which is a fully connected layer, basically, right? It's a linear layer. All right, and yeah, again, as a reminder, right? So the output is going to be weighted average over the value, okay? So why do you want to split the key and the value? Let me give you another motivation, right? Imagine that you're searching the Google for an answer. You wonder how many students are there at NAM in the fall of 2022, right? So you imagine that what the Google engine has to do, it has to fetch the related web pages first, right? It first has to figure out the web pages that are related to your question, right? And then it needs to retrieve information from that web page or those web pages for the numbers, right? So do you see what I mean now? So one is basically keying in and one is returning the value you are interested in. And they don't have to be, retrieved in the same way, right? So that's why, it's one, example to motivate you that, well, indeed, it's one input, but there are two tasks involved. One is retrieving the information or aligning your query sentence to different web pages. And the other one was returning the value, that is, getting the numbers you need at the end from those web pages that are paid attention to, right? That are retrieved. So these are different. Okay, so now let's look at what this self-attention look like, visualize it. So again, as I said, right, so you have X that are split into key and values through fully connected layers, right? And you also have them split into queries, okay? First, we calculate the alignment between the keys and the queries, okay? Imagine that this is a sentence I wrote into the Google search, and then these keys are the web pages, okay? And then, I go through this alignment, which is nothing but scaled dot product, right? Then go through this softmax. This E output will be a softmax, and then I have this attention matrix, which add up to 1, right? And then I know, this how much attention I put on each feature. Right? So in this case, it's a feature map, right? So I have V0 multiplied by this and add by V1 multiplied by this and plus V2 multiplied by this. So we multiply horizontally and add them vertically, and at the end we get Y0, Y1, and Y2, right? That's what we have here, which is mathematically expressed here, right? All these are very simple matrix products. And and now we can do something more, right? So far I've been talking about attending, input attending to itself, right? This layer is like attending over a single input X, right? Right? We could actually attend over multiple inputs or sets of inputs, right? So for instance, so let's look at this example, right? For one problem we're having here. I think I showed this. I talked about this in words a few slides back, right? So we said that our attention mechanism in general, and in this case self-attention, is actually permutation invariant. In other words, if you change the order, and then the output would also just change the order, right? Using the self-attention, right? So, so in other words, there's no order information really considered, right? So one question is, if you want to do this, attends over sets of inputs and encode the ordered sequences like the language, how do we do that? One simple idea, we'll talk about it again later on in a different context, is called positional encoding, okay? Positional encoding is very simple, basically saying that, well, this self-attention layer does not consider the order across these different inputs. What if I add additional inputs? Imagine that each position has an additional feature which is telling its position, okay? So that's why it's called positional encoding. So I have an additional feature, right, to tell the position, P sub j. For each X sub j, I give a P sub j, okay? And how do you give this positional encoding? It's going to be a function position of j. It's not exactly j, okay? It's not like 1, 2, 3, 4, 5, 6. You cannot do that, right? Why? Well, because there's something that you want out of this function that cannot be simply satisfied by using the index 1, 2, 3, 4, 5. Okay? So what do we want or desire out of this positional encoding function? First of all, it should give a unique encoding for each time step or each word's position in the sentence. That's for sure, right? Otherwise, true words or true characters could have the same positional encoding, then there's no order between them. It's very confusing, right? So that should be unique. Okay, you could tell the two positions differences, right? There's no tie. Secondly, this distance between any two time steps should be consistent across sentences with different lengths. So in other words, if you do this mapping, right, and the resulting two time steps, right, the position of I minus position of j, this so-called distance should be consistent no matter what's the length of the input sentence. If you could have a long sentence, short sentence, but this distance should be consistent. Okay? That's another reason you probably don't want to use just 1, 2, 3, 4, 5. And thirdly, right, our model could generalize to longer sentences without any efforts, but still, you want these to be bounded. This positional function, its output should be bounded somehow. Okay? And lastly, you don't want anything stochastic here. It should be just deterministic. Okay? So these are what we desire out of this positional encoding function, right? Remember, we want to enforce the position. So that's why you have one thing you have to think about now, right? We talked about the sequence or text processing, but when we go from the attention to self-attention, we actually removed this recurrent and sequential flow. You see here? Do you see here? Right? There is no information flow going this way. Okay, that order information, you see that because we are using all these, matrix product, these linear layers, there's nothing really, enforcing the order that we used to have. Okay, that's something to think about. Okay, so in other words, it doesn't really automatically consider the nature of your data. In this case, it's a sequence. So the positional encoding solved that issue by introducing such a function, additional positional encoding. Okay, and there are different options. You could have a lookup table to learn, and then sometimes it's a fixed function with whatever you desire. For instance, in the first paper that brought attention to our attention, right? Vaswani, NeurIPS 2017, attention is all you need. They used this sine, cosine, this sinusoidal positional encoding, where the frequency is determined in this way. Okay, I think the positional encoding is a very tricky thing, and in protein structure prediction, for instance, people tried to generalize AlphaFold 2 from a single protein structure prediction to protein-protein structure prediction, right? The first thing they did was actually a straightforward choice, but not necessarily correct. They were basically saying that, well, imagine that I'm folding a very long sequence by concatenating the two sequences together. But I try to tell the model that these two sequences are not contiguous. Between them, there's a gap, and then I use positional encoding to tell them. Okay, that's one way. Your model are trained over single protein structures, but it can be applied to multiple proteins when you introduce the proper position encoding. Okay, so that's one thing. And this is the positional encoding. And another thing of a generalization, right, is masked self-attention layer. So that's something also related to the fact that we lost the order, right? One way is you can include the order here, okay? Positional encoding from the input. Another thing to enforce the order is to constrain somehow this alignment function or the alignment scores, okay? In other words, right? In other words, you are preventing, right? For instance, when you are querying Q0, you are only allowed to use key 0. And you are not allowed to use key 1 and key 2 because they are in the future. This is the present, this is the future if t equal to 0, right? So for the first query, I'm only allowed to look at the first, x0. Because when t equal to 0, looking at this vertical line, t equal to 1 and 2 are futures. So their values would be minus infinity. Okay? Why use that one? Because I'm using the softmax. I'm going to use exponential. So that attention is going to be 0. All right? That attention is going to be 0. I'm not going to pay attention to future. All right? So this is essentially introducing a causal system. If you're familiar with, signals and systems, this is essentially a causal system, isn't it? Right? You're not allowed to use the signature from the future, right? And similarly, if you look at the Q1, I'm aligning to just the past and the present, but not the future, okay? And similarly for Q2, the past, 0, 1, and the present, Q2, okay? No future. So this is done by manually setting the alignment score to minus infinity. Why do we do that? You remember we use the exponential of the score and do the softmax. That essentially gives us a 0 attention right here, 0 attention. So you don't pay attention to the future for each given t. Okay? So that's what so-called the masked self-attention layer. Another thing is, so basically I'm talking about a Vaswani 2017 paper, right? So I talked about self-attention in general, but there's also masked self-attention, and there's a multi-head self-attention, right? So these are essentially what Nami introduced the last time, but we didn't have a time to talk about the details. So here, what is a multi-head self-attention? Basically, you're not using a single self-attention, but multiple self-attention layers, and then add or concatenate. It's very simple. Okay, so I think in the original paper they used 6 or 8 of them, right? The layer is 6 or 8. 8 has and the 6 layers, right? Right. So you could have this parallelization of multiple heads, of multiple self-attention, and you call them multiple heads, right? And then you can stack the layers as well, okay, vertically. And then, now you have something in mind that, the difference between the, general attention and the self-attention. Basically, in the general attention, you have input that will be split into the keys and the values, and you also have a query, right? In the encoder-decoder system, the query is from the decoder, and the input is for the encoder. But in the case of self-attention, you could introduce a so there's only x. Your q's and k's and v's are going to calculate by x. Again, it's by 3 kinds of linear mapping, right? Key, value, query, they are all mapped from x linearly through the fully connected layer, right? So it's all to be learned parameters. Okay, so that's why we call it a self-attention. Okay.